Hello, it's a wonderful day at Basin Safety Training and Consulting. This month, April 2020, we're going to be covering lockout tagout, also known as isolation of hazardous energy, electrical safety, and ground fault circuit interrupters, also known as GFCI. These topics kind of merge together and collate as they're all very relative to one another. Most of them fall under the OSHA Code of Federal Regulation, CFR 1910-147. Don't worry, we're not going to focus on those numbers. Just know that that's the topic, the OSHA regulation that we're primarily focusing on. We're also going to talk about written lockout tagout programs and how they're designed to protect you and involve a lot of the elements of this training. Your internal operating procedures, we're not going to go into specifics, but that you need to have them depending on what type of equipment you're working with, as well as equipment manufacturer recommendations. So some objectives we have today: understanding the requirements of the lockout tagout standard, various types of hazardous energy, review different types of lockout tagout devices, understand the requirements for lockout tagout procedures, and also being accountable to your lockout tagout program. So why do we care about lockout tagout? What's the purpose of it? In our industry, there's a lot of hazardous energy that can be uncontrolled. So the goal of lockout tagout or energy isolation is to isolate that energy and control it so that we're not worried about people being exposed to it. The way we do that is by using locks and tags, but that's not the whole program. That's just one element of a lockout tagout program, and we'll cover the 7 steps of the program in a little bit. So the lockout tagout standard requirements are pretty straightforward. They have a few different elements that every company that has equipment that needs to be locked out have to follow. So 1910-147 says each company needs to have a plan with specific equipment that needs to be locked out identified in that plan. It can't just be a generic, we wrote this up once and it applies to everything. It needs to be specific to the equipment that you own. Employers also must give locks and tags to employees. Provide procedures, like this is step-by-step how you lock this out, and then also provide the training. If you have authorized, affected, or other employees, you have to train them. Most employees are going to be other by nature, but like for instance, our company, we have one authorized employee to perform work on energized equipment, and he's our mechanic. He has DOT certifications. He's been trained. So he's authorized, but not to work on the electrical systems themselves, just the equipment that becomes energized. So there are some exceptions to this rule. It's not required if hazardous energy does not exist. If something's being performed during routine operations, for example, removing a filter sock, in a saltwater disposal, you wouldn't need to, even though water coming through is a hazard, we close the valve, that's a routine operation. Cord controlled devices that can be unplugged, we don't need to worry about it then. And also hot tap operations where shutdown is not possible. But there are additional procedures that will be involved in that. So there's different types of hazardous energy out there that we work with every day. Electrical is a very common one, stored mechanical, moving machinery, steam, springs, gravity, pressurized fluids, chemical energy, and then as well as nuclear, which is a little bit more rare up here where we're doing our work. So different types of equipment that require lockout tagout. On the electrical side, accumulators, saws, pumps, production equipment such as treaters and separators, fluid systems, motors, heaters, a million different things require lockout tagout. And once again, your plan needs to recognize those types of equipment in your program. So there are certain instances where things can't be locked out. There's no, lock receptacle to in order to place a lock. So in those cases, you need to remove critical components, if possible. For example, in a vehicle, attach chains and cables. I'm thinking of a pumping unit here, to lock out the weight so that they don't spin. You set them and then chain them out so that they can't move. That's just another example. Or also create barriers and enclosures so people can't enter into an area where energy could be released and hurt somebody. So the main components of a lockout tagout program, or its fundamental elements, are each employee will apply their own lock and their own tag to the equipment being locked out. Tags can sometimes be multiple use. Like, for example, if you have a multi-lock hasp with 10 different locks on it, it's possible to use one lock or one tag rather, as long as each lock is identified. The lock that applies will only have one key and it will be in their possession. The energy cannot be released accidentally or purposefully until all locks have been removed, and this ensures that all employees are out of danger before any energy starts moving again. Lots of different types. I mentioned multi-lock hasps here earlier. That's where multiple people can lock it out. That's our first image there on the upper left corner. Valve covers, chains, multi-lock hasps, again, blocks, ball valve covers, piping blanks, and you can see some different examples here of a piping blank in the upper right-hand corner. Another multi-lock hasp, it's kind of a triangle multi-lock hasp for the valve there, the ball valve, and then a cord cover there on the bottom right. So guards can also be used as locks. I showed this before. You have washing machines, lawnmowers, car washes. Essentially, each of these systems use an interlocking guard to protect from hazardous energy. So the washing machine, obviously, once you turn it on, a little button sinks in there inside of the mechanism and prevents the door from being open so that no one can get in, water can't flow out, etc. Lawnmowers, same thing. There's a weighted there's a weight sensor on the seat, so if it's not depressed, the lawnmower won't move. Definitely ran over a lot of people in the years where that mechanism came from. Car washes, on the automatic ones, you have a door opening and closing as cars come in and out. There's a sensor that triggers once a car passes a certain point, and then it's safe for another car to come in. And you may say, is one car hitting another car an energy isolation thing? And absolutely, kinetic energy is a thing, as well as gravitational. So anytime one object can strike another, or the energy from one object can impact another, we want to use lockout tagout. We want to protect that energy from causing harm. So a few other requirements we talked about. Everyone needs to have their own lock, their own tag. They need the locks also, the tags rather, need to be durable, standardized, substantial, and identifiable. So it doesn't necessarily have to look like these tags here, but they have to follow these requirements. And if you're going to use your own printed tag, no problem. You see some of them have stripes through them, some of them don't. The danger sign usually needs to be on there, or warning. In those cases, they do have to follow the ANSI specifications for the lettering. So you can't just write it with a Sharpie marker, for example. So getting into the employee responsibilities and the different types of employees. As I mentioned earlier, an authorized employee is an employee who can maintain equipment, perform the maintenance on the equipment, and then also do the detailed inspections. They need to be trained specifically as an authorized employee. You can't just be like, for example, our authorized employee was a DOT mechanic, which is fantastic. We still need to train him specifically on our equipment, regardless of his training and certification prior to coming to our company. So their responsibilities are to place the lock, place the tag, communicate with all the other workers when maintenance is being done, repair the equipment as needed, and then remove it when the job is completed. Affected employees are employees who may work or use the equipment, but not necessarily perform maintenance. Our air compressor, it fills breathing air cylinders, so it's a dry grade D air. A lot of people can use the equipment. Only one guy can work on the equipment. So they'd be the definition of an affected employee. They need to understand the requirements of the lockout tagout program, leave the devices alone if things are locked out, notify personnel when equipment needs maintenance, and then also follow the safety rules regarding that equipment. Other workers are workers who, for example, in our instance, do not use the breathing air equipment, but maybe work around it. So our receptionist does not fill breathing air cylinders, for example, but she still, because that equipment exists in her work area, she still needs to be trained on, hey, you see a lock, you see a tag, don't touch it, stay away. It's a very basic training. It doesn't have to be 5 hours or anything. Going through this training, for example, would cover the needs for that employee. So they may be there, informed about the lockout tagout, and then if they see anything, they say something. So I mentioned the 7 basic steps. There's 6 steps to the process, and then the 7th, which is performing the maintenance. So we have number 1, notifying employees. Number 2, shutting the equipment down. Number 3, isolating the energy. So we let everyone know, hey, we're going to perform maintenance on this equipment. Then you'd shut it off. You hit the power button to shut it off. Isolating energy typically means throwing a knife, tripping the knife throw, disconnecting the circuit, pulling the breaker, whatever you have to do. Then you attach the lockout device. So in this example, in the process, attaching the lock is the 4th step. We've already, completed 3 before we even attach the lock. Then we release stored energy, typically, which is done by trying to turn it on or bleeding it off, whatever we have to do. Maybe there's a half a revolution left in a fan blade, or some electricity left in there. Then we're going to release that. Verify the lockout. I'm like a double, triple try guy where you keep testing it just to make sure nothing's getting. Basically, you try to turn the thing on at that point. And then lastly, you perform service and maintenance. So those are the 7 steps of a lockout tagout process. All right, so if you have multiple people that need to lock out, as I mentioned earlier, you can use a hasp, or you can apply one lock onto the equipment, take the key to that lock, put it inside of a lock box, and then have multiple locks lock out the box, which for me is typically the simplest. It's less stuff out there in the field. You can kind of control that lock box a little bit easier. So that's a good method. But that way it ensures that each person on the lockbox needs to remove their lock before the ultimate key can be taken out to remove the primary lock. So tagout system, as I mentioned, everyone's kind of supposed to have their own tag. If you don't want 20 tags on a piece of equipment, you can use one tag where all the relative people are identified. They are not a substitute for locks, though. So you can't just put a tag on it and be like, yep, don't use this, because tags can be removed. They're not permanent. They don't need a lock or a bolt cutter to get the equipment running again. In fact, in some instances, the equipment can be turned on when a tag is in a lock receptacle. So it is not a substitute. They can only be removed by authorized people. So the authorized person places and removes the tag. And then once again, they have to be legible. A lot of times guys use Expo markers or Sharpie markers with a fat tip. Those are difficult to read a lot of times. Like I've come upon a lot of these where it's, I think it says Tom, it may say Tim, Tam, I can't really tell. And then the phone number's etched in there. And it's very difficult to read. So try to use if you are using a Sharpie, try to use a fine tip Sharpie so that the words are legible. So if a lock needs to be forcibly removed, for example, somebody went on days off or got sick, went to the hospital, that can be done. However, it needs to be done with documentation. So every effort to contact or get the person to remove their own lock should be done. And finally, after documentation and every effort's been performed, then you can remove the lock, and it has to be an authorized person that removes that lock. So the standard, obviously we have the OSHA standard, then we have our company policies, then we want to document the process. So it doesn't have to be complicated. There's forms for it out there, but I wouldn't care if you used a legal pad to document, separator, changing out the float inside. So what are your steps? Well, we locked out the inlet valve, we locked out the outlet valve, we locked out the gas valve on top. We locked everything out. You document that, and then when you're done, remove lock 1, remove lock 2, remove lock 3. So we want to document every time we perform a lockout tagout process. All right, so that's all for lockout tagout today. Next, we move into electrical safety, which once again, as I've already mentioned, lockout tagout definitely applies to lockout or to electrical safety, and we'll discuss that here in a little bit. So the objectives for this topic are learn how to protect yourself against electrical hazards, know what they are, know the difference between qualified and non-qualified workers, understand the different hazards associated with electricity, and be prepared for an electrical emergency. What do you do if something goes wrong? So terminology, we have current, resistance, voltage, conductors, insulators, and grounding. These are the most common terms. So current is the movement of electrical charge. That's in everything. Resistance is anything that opposes the flow of current. So certain equipment are called resistors, and every wood has a different resistance than copper, for example, which is a much higher resistance. Voltage is a measure of electrical force. Conductors are substances that have little resistance to electricity, such as copper. Insulators are wood, rubber, or glass that insulate the electricity from coming out of the conductor. And grounding is a protective measure that transfers rogue electricity into the ground rather than sparking at the receptacle or at the tool. So two different types of categories, similar to lockout tagout, a little bit different. Qualified electrical worker is someone who has training and knowledge to work on around alive electrical parts and equipment. Typically, they've attended NEC courses, have a journeyman's license. It's not just like, oh, yesterday I was unqualified and today I'm qualified because I took a test online. It's not like becoming a minister. Like there's actually some specific training that's required. And unqualified workers is pretty much everybody else whoever has not received those trainings. So some quick facts on electrical safety. Most recent data available in 2018, 160 workers were killed by electrocution on the job. If you go back 8 years, 2010, 157 workers were killed by electrocution on the job. So the statistics are staying pretty steady. But if you think about it, that's like half a worker a day being killed by electricity in America. So this may seem like, oh man, this is pretty basic stuff. Still, there's a lot of people untrained making decisions about electrical equipment that don't follow process and procedure. And these procedures will keep you safe. You don't have to be one of these 160 workers. And that's just people that are killed. There's a lot more injuries that happen around electricity where fatalities are not and don't happen. Main types of injuries, you have electrocution, which is death due to electrical shock itself, burns, which are very common, and falls. Actually, one of the most common fatalities outside of electrocution is people being on a ladder and falling, or being at heights and falling. Once they're shocked, they lose control of their footing, and then they fall. So electrical shock happens when current passes through the body. Severity depends on three different things: path of electricity through the body, amount of current flowing through the body, and length of time the body's in the circuit. A lot of people say, and it's true, that it's not the voltage that kills you, it's the amperage, which is true. So your body is a conductor of electricity. The electrical system of your body is the heart, or the nervous system is actually an electrical system. So when it comes into contact with electricity, it pulls it. And those are amps that it's drawing into the body. And so the voltage could pass through you without doing any harm, except the electrical system, your heart specifically, is going to draw the amps from that electricity, and it's going to overpower the heart, just like it would, if you have 480 volts running to a 120 volt system, the amps are going to destroy it. So low voltage does not equal low hazard, once again, because of the amps that your heart is drawing in. So shock happens. A defibrillator is typically needed when that happens to reset the heart at the correct voltage. So anything greater than 2 amps can cause ventricular fibrillation. It can cause death within a couple minutes unless it's reset, or once again a defibrillator is used. And a small power drill, just for example, uses 4 to 8 amps, which is nearly 400 to 800 times more than what's required to cause ventricular fibrillation. So, we use these tools every day. We don't even think about it. You plug in a cord and go to work. But, there's been a lot of people that have been killed by this equipment in the past, and there's some safety measures that we're going to talk about here in a moment that we've created, or the industry's created, to prevent those injuries. So electrical shock, once again, that's what happens when current passes through the body, or energy passes through the body. If energy does make contact with you, you will receive a shock. And if maybe you've never been electrocuted by tools or equipment, but maybe a knife in an outlet when you were a kid, electric fence. Most of us have experienced what a shock feels like, and it is not pleasant. Burns happen when, obviously, the amperage comes into contact with your body, heats up the blood vessels enough to burn, or the skin. Any organ heats up to a certain extent. The problem with these injuries is they're internal, meaning they start at the center of the vessel, or the center of the skin. So the damage is deep, and it is permanent. It's pretty serious. So typically occurs in the hands of people where they're working around electricity and very serious. And this can happen from arc flash or, once again, being shocked. And we'll talk about the arc flash in a little bit. So falls happen, obviously, when you come into contact with an electrical conductor that is live or energized. You get a shock and then you fall because you lose control of your center of balance, center of gravity. So that's one of the most common indirect injuries that happen with electricity. So if you're working at heights, definitely make sure that you're tied off for one, and absolutely make certain that your equipment is locked out and tagged out. So an arc flash, as I mentioned, essentially happens when electrical current heats the surrounding air, rapidly causing an explosion. So the oxygen in the air, is not typically flammable unless temperature gets to a certain degree. Arc flash reaches that temperature, heats the oxygen in the air, and the air itself becomes flammable. That is obviously a problem if you're in the near area because the heat signature on that is intense. It has to get extremely hot, thousands of degrees. So electricity will then follow that superheated air, and you can get electrocuted and burned all at the same time. Pretty serious stuff. If you work around high voltage electricity consistently, definitely make sure you get the arc flash training. We offer it here at Basin Safety. It gives a lot of specifics on how to prevent a flash from occurring. So overload hazards. This is something our parents told us about when we were a kid. You don't want 50 things plugged into one outlet. What can happen is, if the circuit doesn't trip, what can happen is things heat up too much, whether it's the plugs or the receptacle, and that heat can burn through the insulation and then cause an arc as well as a fire. And we've all smelled kind of the heated electrical insulators before. So ground fault circuit interrupters are another device used to protect from this. Essentially what they do is they protect from shock by detecting any nominal difference within the electrical circuit known as a ground fault. So if there's any leakage, for example, you have a cord plugged into a wall, the insulation is cut or burns through, and something comes into contact with that electrical wire, there's going to be leakage to that item, whether it's a person, a piece of equipment, etc. There's going to be less voltage coming back to the circuit than is leaving the circuit because some of it's leaked. In 1/40th of a second, that GFCI will turn that system off once it determines or notices that leak. Water is one of the main things that will draw current, and that's why you typically see GFCIs in bathrooms. Nowadays, they actually have these as a part of the breaker system. So it's a GFCI breaker, meaning it's doing both at once. And then so in a lot of newer homes, you won't see the outlets that way because the circuits themselves are also GFCI. Static electricity, another big issue in electrical safety. Not something we typically think about as electrical safety, but it is. Basically what happens when you get static electricity is you have two items that come into contact with each other that have a different charge or a different potential, as we'd call it. So it can cause fires in areas with flammable vapors, fumes, flammable dusts. Obviously, in those areas, you want to use caution, have an LEL sensor, and never assume LEL environments are safe because static electricity is possible. So top of a tank battery, inside of a treater, etc., static electricity can happen. So if there's an LEL, never be like, oh, it's pretty low. Definitely, clear the area before you continue working because static can happen at any time, and more commonly in the winter because the air is less moist, and moisture essentially draws some of that current and prevents static from happening. But when you have dry air, static electricity is a lot more possible. In fact, inside of transformers, you need to have dry air so that essentially it works properly and the electricity moves properly. So you have to, when they do work on a transformer, they have to essentially purge all the air and the moisture and then pump in dry air to make sure it meets the parameters. So overhead power lines, major issue. Minimum distance for overhead power lines is 10 feet, and that it increases as voltage increases. So one major issue is they're not insulated, meaning there's no cover over them, and coming into contact with them, you will become part of that system. Power line workers have special training in PPE in order to work around them safely. Obviously, they'd be considered qualified. You don't want to use a metal ladder around power lines be very careful with cranes, rigging around power lines, heavy equipment, excavators, etc. Electrical shock can happen very easily with these. Ladders and scaffolding, pretty much anything 10 feet minimum distance, because they can arc to you if you're working with conductive material. So grounding, another major issue in electrical safety. As I mentioned earlier, it essentially takes any rogue energy and then disperses it into the ground because the ground has moisture in it. So the path to ground from circuits must be continuous, and the ground wire needs to be designed to needs to have essentially low resistance. It needs to draw that energy. So there's a violation here. Someone removed the grounding plug probably because the receptacle or the outlet didn't have a grounding plug in it, so they removed it. And that's a major issue, because if there's rogue electricity at that point, it won't travel to the ground, it will travel to you, because you have once again an electrical system that wants to draw energy, and you're 70% water, so electricity is going to want to flow to you at the path of least resistance rather than to the ground. So an assured grounding program is a qualified electrician install and maintain the equipment. Most of us have this program basically saying, hey, if you don't have training, you can't mess with the electrical systems. And it's not a bad idea to have that. This is also known as a 3-wire grounding system. Basically, you have the plug on the bottom that is the third cord that draws any rogue electricity to the path of least resistance, which would be the ground in this case. So double insulated tools, we're going to talk about that a little bit. So inside of every tool, obviously it's electrical, it has an electrical system. A double insulated tool has an insulation feature outside of that system that does not come into contact with it. There's no electrical connection, meaning you can hold the handle of that tool and in no way be connected to the electrical portion of that unless there's a failure inside of the tool. Old tools, as many of us remember, and my grandfather had a plethora of these, had a metal housing, which was a lot easier, I don't know, probably cheaper back in the day. So they used metal housings. Well, the problem there is it's impossible to prevent a connection if you have a metal housing. So they changed that up, and these tools need to be rated, and they typically will have this little symbol right here. It's a box inside of a box, essentially showing that there's a space between the electrical conductors and the housing of that equipment. So handheld electrical tools are typically going to have this. That's just going to be that separation. They need to have 3-pronged cords with groundeds and plugs to be grounded to receptacle, be double insulated, or be powered by a low voltage isolation transformer. Once again, just another protective measure. So there is some debate about brushless tools and intrinsically safe tools. And I've actually had this wrong in the past, but brushless tools essentially do not generate high volumes or any sparks. So they're designed to be kind of spark free, right? Because you don't have a brush in there creating sparks, which is good. It prevents, sparks from happening inside of the equipment. Intrinsically safe tools, however, do not allow any heat outside of the system either. Not just, sparks, but heat as well, which can cause combustion. So intrinsically safe tools are tested in environments with LEL and are also certified not to create heat or sparks that could cause ignition. Both, not just sparks, but heat as well. So they are not the same. An intrinsically safe tool needs to be marked intrinsically safe. It'll say that on the equipment, usually in the data plate where the serial number is. All right, so cabinets, boxes, and fittings. So you have junction boxes where multiple, electrical wires come together and either are connected or terminated. Unused openings in cabinets need to be covered. They have knockouts in them. Those little quarter-looking things are called knockouts, and they should be kept clean and good condition. The covers should be, in place. Dust shouldn't be able to get in there. Birds, spiders, mice, etc., which, as we've seen I've seen many times, they will make their home if there's any way for them to get in there because it's warm and nice and cozy. Flexible cords, one of the bigger OSHA violations out there and fire inspection violations include flexible electrical cords. So essentially maximum of 90 days can they be used, so they can't be used to have things plugged in permanently. Cannot be used in place of fixed wiring and are vulnerable to aging and physical damage. That's kind of the reason. Nicks, cuts, they get brittle, old, they change color. Most of us have seen this. There's an episode of Parks and Recreation. If you haven't seen it, There's a guy named Ron Swanson who's like the OSHA violation king, and there's an episode where the city inspector comes to his shop and he's basically he's fused and used a flexible cord to wire his entire shop. The guy about has a heart attack and basically says he needs to redo the whole thing. And I've actually heard of this happening in many cases. People have used these for that purpose. They are not designed for permanent wiring because they do get old, brittle, burn through, have issues with the plugs, receptacles, etc. So other flexible cords that can be used permanently are actually connected directly to the electrical utility. So, for example, lighting fixtures, pendant lights, etc., where you have a cord hanging down, those are all fine because they're designed for that purpose. But once again, electrical cords, extension cords are not the same. So they can't be used as a substitute for fixed wiring, can't be run through walls, ceilings, floors, etc., and cannot be concealed behind or attached to building surfaces. So they can be hanging, on hooks that aren't like, not zip ties, but just on hooks, but they cannot be permanently attached to walls or ceilings. So some red flags, obviously if a circuit breaker keeps tripping, don't just keep flipping it back and using the tool or equipment. There's a problem. Something needs to be fixed. Blown fuses, warm tools, wires, cords, connections, or junction boxes. Obviously, the smell of burning rubber is a pretty good sign something's wrong. If your GFCI keeps tripping, and then also, worn, frayed, scratched, or scorched, or blackened insulation around a wire connection, these all are red flags that something needs to be changed, whether it's the cord, the tool itself. Sometimes the circuit breakers or the fuses can go bad. In those cases, change them out. Don't keep using them. So electrical lockout tagout, we've already kind of covered lockout tagout in our previous topic, but obviously this is the best way to protect people from being exposed to electricity. So the main way that we protect people. We definitely need to use it and follow the 7-step lockout tagout process in order to effectively protect people. So PPE is also different with electricity. Even the FRs that we use are different. So with oil and gas, we use an NFPA number that's different than the electrical one. The electrical one is NFPA 70E, and that's the one that's designed for electricity. Type E hard hats, which are rated to 20,000 volts. Fortunately, in oil and gas, most of our hard hats are Type E. So if you look on the bottom, on the brim, it'll tell you what type of hard hat it is. Insulated gloves are also a necessity. A lot of times face shields and non-conductive hard toe boots, so not steel toe, for example. Other equipment, insulated blankets, rubber or dielectric mats, and they can be under equipment, under where workers are working. Even with hydrovacs, these are recommended as, you can use a hydrovac truck and, expose, electrical systems. But touching a metal hose, spraying an electrical unit, standing on the ground, you can become part of that circuit and be shocked or electrocuted. So using a mat kind of prevents that connection from happening. All right, work in wet areas. Obviously, using electrical tools and equipment while standing in water, not a great idea. Some pretty easy ways. You can use elevated platforms, non-conductive work surfaces such as rubber mats, not pallets, obviously, because wood is conductive, especially when wet. Stone, etc., to prevent you from coming into contact with a potential circuit. And obviously, lifting the tools and cords out of the water, also an important component of this. So don't work around or with equipment. If you're wet, it's wet, anything's wet. You want to make sure everything's dry, as it is the intended atmosphere to work around electrical equipment. So lastly, before you work on equipment, or even if you're authorized, you want to test it. And I'm like a 3-try guy. I like to test things out at least 3 times, as well as using essentially a voltage meter, right, to test the equipment. So you're going to use that, make sure that it's actually, terminated, or as they'd say, a closed circuit rather than an open circuit where electricity is flowing. So that wraps up our electrical safety and GFCI section here. So if you're not qualified, you're not working on it. Electricity can be deadly and cause serious injuries, burns, heart failure, obviously, fatality. Electrical systems can cause fires or explosions as well, so damage to equipment and buildings, etc. And always guard and disconnect electrical systems when you're using the equipment for maintenance, or you're having to work around electricity, but you don't want to be impacted by it. So that's all we got for this month, April 2020. It's a beautiful day at Base and Safety, beautiful day in North Dakota. Thank you all for tuning in, and we'll talk to you next month.